Hello, students. This begins a series of videos that will lay the foundation for Equilibrium Unit 4, which focuses on what we've always called insoluble solids. So we want to be sure, if you see it on the left there, that by the end of these teachings, that we understand what all of those mean and represent and can problem solve with them. So if I could refer to our student note packet for a moment. What are we even talking about here? All right. Usually, we encounter insoluble solids when we are making precipitates. So recall that we have solubility rules. And in your student note packet, there's a summary on page 10 of our main rules. So you know there's our always sodium compounds, always soluble, nitrates, always soluble, potassium. Those are the main ones that we revisit again and again, where chlorides and bromides and iodides, except for silver, lead 2, mercury 1, those are going to be soluble. So here's just a reminder. Now, usually in this unit, the wording of the problem will help you out with the solubility rules. But we know that if we have a sodium compound, that if that is placed in water, that it will have dissociated. We know that 100%. And so it's very rare that we're going to find any sodium and chloride formula units. The majority of them will be separated and then solvated and surrounded by water molecules. Although, once and again, these guys will collide and reform that. We know the overwhelming majority will be found as separate ions. However, if it is insoluble, for example, lead 2 chloride, up until this chapter, we would say, well, then this doesn't dissociate. Okay. So if we can remind ourselves about precipitation reactions, precipitation is when you combine 2 or more solutions. And so they could be colored, but you can see through them. So 2 or more solutions, and we know sodium compounds are all soluble, so this will be separate sodium and separate chloride. All potassium compounds are soluble, so separate potassium, separate iodide. All right, double replacement. So we would say we're going to form potassium chloride and then sodium iodide. Well, if we would continue with the net or the ionic over here. So we understand that when we add these together, so this beaker has separate sodium and chloride. This beaker, separate potassium and iodide. Okay, when we combine them in the same beaker, well, we know all potassium compounds soluble, so these will be dissociated, and all sodium compounds soluble. These will be dissociated. So actually, we have not accomplished a driving force. These will just be spectators, and so no reaction. We know that it's either that we're forming a gas or forming a precipitate or forming water or transferring of electrons. But here, so double replacement, PbI2 and KNO3, and we need a 2 there. Well, all potassium compounds are soluble, and halide compounds are usually, except in the case of lead plus 2. And so the creation of this is our driving force. We would have separate, because all nitrate compounds are soluble, separate ions. We would have 2 potassium and 2 iodide in ratio. These are all aqueous, 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 aqueous. And we understand that if these are in our first beaker, and then we combine them with these, when the lead encounters the iodide, we get the creation of this ionic compound that we would say is insoluble. And so the net ionic would be the lead ion reacting with two iodides to create lead 2 iodide. There's our driving force. So we talked about these kinds of things in Unit 4, reactions in aqueous solution. All right. Usually, whenever a precipitation reaction occurs, there is a nice visual. In fact, this creation of this gorgeous big bird yellow compound is lead 2 iodide, that very characteristic color. And you start with the two clear solutions, but then as they get added together, you're creating that yellow, no longer clear because it's insoluble solid. Here's another representation. And so we said, you know, in the first beaker, they would be separate ions, second beaker, separate ions, but then when the lead and the iodide find each other, they collect and then eventually fall out of the solution. Usually, precipitates are white because so many ionic compounds are white. And so if we witness a cloudiness when you're performing a reaction between two solutions, we know it's a precipitate. And here, just another image, you know, even though it's mild cloudiness on the left, we would still say a precipitate has been formed. And then we know that upon sitting, the solid will fall out of solution. Okay, and it appears as if nothing is going on. Well, that is not exactly correct. Okay, and here is where we begin our understanding. Okay, so if we're looking in the student note packet, we want to make sure that we are clear as chemists when we use the term solution, a homogeneous mixture. They're physically combined and can be physically separated, and there's equal distribution throughout. Solvent, what does the dissolving? Solute, what is being dissolved? Solubility. Solubility is the maximum amount of solute that can be dissolved in a given amount of solvent to make a saturated solution. The solution is holding the maximum amount of dissolved solute that it can at that temperature. Solubility is usually referenced as mole per liter, mole of solute per liter of solution, molarity. Sometimes we can see it as gram per liter, but usually this is how it's being referenced. Supersaturated, your solution is holding more dissolved solute than it should at that temperature. For example, sweet tea, and you actually, remember, make a saturated at a higher temperature and then cool it down. And if it's stable, it'll become supersaturated. And unsaturated, you can still dissolve more. It is beneath the saturated point. Okay, well, again, when we combine these, we get that big bird yellow precipitate. And we observe that collect in the bottom of our beaker. And it seems like nothing is going on. But actually, what we understand and measure is a small amount of this is dissociating and creating the separate cation and separate anion. We can measure these in solution. Now, the majority we can visually see is existing as solid. But when we measure, we can actually detect the presence of these very, very small concentration. So we understand that this is equilibrium. So of course we would have a Ksp expression. Well, I'm rushing to Sp. Well, first it's K. All right, remember, only things that are aqueous and gaseous affect the equilibrium position. So our reactant does not. Remember, law of mass action. So we have our cation to the first power, and then our iodide to the second. And that would be over 1. Because it is describing what we know is the behavior of an insoluble solid. So there's really no such thing as being truly insoluble. A very small amount of it is dissociating. But also, some of this is finding itself and recreating the ionic solid. These values are much less than 1, much less than 1. So we're talking 10 to the minus 10th, 10 to the minus 32. It's very, very small amounts, but enough, for example, to cause a health consequence, possibly if it's in our drinking water. So because of this being applied to describe insoluble solids, we call it Ksp, the solubility product constant. The solubility product constant. Now, Ksp is not solubility. It is the equilibrium expression from the equilibrium of an insoluble solid. All right. Again, these are dynamic. We know all equilibrium is. And so if we could envision that even though we see that yellow at the bottom, it is dissociating the ions at the same time that they are recollecting. Ksp is describing the solution at equilibrium when it is saturated. So even though it's an incredibly small amount of ions, we understand it's creating a saturated condition. All right, so let's dig into our first example. Copper 1 bromide has a measured solubility of 2 mole per liter at 25 Celsius. Calculate its Ksp. Okay, we will always reference the ionic solid as our reactant and just acknowledge that we understand a little bit of this is dissociating, and it's a 1-to-1 ion ratio. Now, Ksp will be copper plus first power because of the coefficient of 1, and bromide to the first power because of the coefficient of 1. All right, we need Ksp, and so we're going to apply an ice table. Just like when we're working with acids and bases, we ignore water because it doesn't impact the Ksp. Well, we ignore the solid. All right. We are imagining, just like we do with acids, that we have just put this into the solution. And what this is telling us is that when equilibrium is reached, the solubility of this is 2 mole per liter. 2 mole per liter. So what we will expect, for every one of these, we get 1 copper plus 1 and 1 bromide. You're not told you're starting with anything else in solution, so we imagine these are 0 and 0. So to get to equilibrium, we know we will make some x, and again 1-to-1, so it's 1x and 1x, and then at equilibrium, x and x. So even though we would not express the solid in terms of molarity, if this is talking about the solubility, this is telling us our x. So the solubility is our x. I was looking in another very common collegiate chemistry textbook, and with Ksp, instead of x, they use s, because our x is our solubility. If that helps you, go for it. Go for it. All right. So we know then that the amount of this at equilibrium is 2 mole per liter and 2, oh, I was wondering why these were such crazily big, 2 molar. Oh, erroneous, ladies and gentlemen. I meant, needed to correct that. That should be 2 times 10 to the negative 4th mole per liter. I was going to say those are big values. So times 10 to the minus 4th and times 10 to the minus 4th. Okay, so our Ksp simply will be x times x, or the 2 times 10 to the minus 4th molar squared, which here, Ksp, and it's a very reasonable value, 4.0 times 10 to the minus 8th. And just like before, we're not concerned about units on our Ksp. So that's a very, reasonable, yeah. Ugh, if I didn't catch my error, to get 4, that would have felt uncomfortable. Okay, so we've learned that solubility ends up representing our x. And if we'd rather refer to it as S, more than fine, more than fine. Okay, let's do another example. Oh, on the next page, I've just shared with us, I mean, look at these values. Oh my gosh. So we're talking about, 10 to the minus 34th, 10 to the minus 38th, 10 to the minus 49th, 52, and so on. So again, whenever we're talking about, these creating ions, they are in incredibly small amounts. We are grandly favoring reactant. So it's not a violation of what we've always called insoluble. All right, let's proceed on to do one more example. All right, calculate the Ksp for bismuth sulfide, which has a solubility. So we know automatically that is our x. That is our x. Okay, just be careful. This is not a 1-to-1 mole ratio. When this dissociates, we will get 2 bismuths and 3 sulfides. Be careful, be careful. So our Ksp expression is the bismuth ion squared times the sulfide cubed. All right, our ice table. Who cares about our solid? All right, but the solubility is referencing that. For every one of these, I make 2 bismuths and 3 sulfides. I'm not told I'm starting with anything else in the solution. So these are going to be 0 and 0. So my change will be plus 2x and plus 3x. So 2x and 3x. Realizing my solubility is my x. So different ways we could do this. To find Ksp, you could just plug in your expressions of x. So this is 2x squared and then 3x cubed. You could get this to be 4x squared and then 27x cubed. And then keep going from there and then just plug in your x. Or we could actually do 2 times 1 times 10 to the minus 15th. And then 3 times 1 times 10 to the minus 15th. And then plug them in and square and cube. So it's totally up to you. But what we should get then as our Ksp, 1.1 times 10 to the minus 73rd. So again, incredibly, incredibly favoring reactant. Okay, so that leads us through and a couple examples and defines kind of the introduction to this unit. And if I'm not mistaken, if I can take a look, I am pretty sure that you could actually complete your first test. Yep, on page 92 after this lesson.